Hi everyone. I am putting this video together to show you how to think through these manometer problems. These problems can be found in the student resource folder, and I've also put them in on campus. These are the very same problems that you would find in the guided notes, except that I split these problems up so that you have some room to work, and I also included a diagram of a manometer that we can modify for the different problems that you see here. Okay, let's just start with one of these problems, and I think as we work through a couple, you'll see how you should approach solving these things. Okay, so first off, I want you to just take a look at this manometer diagram right now. So as this manometer is drawn, the mercury level is the same on both sides. If that was the case, right, that would mean that the pressure inside the gas container equals the atmospheric pressure on the outside. Notice that this is an open manometer. So at the open end, the contents of that manometer are experiencing atmospheric pressure. So as this is drawn right now, the atmospheric pressure would equal the pressure inside the container. Now, if the pressure inside the container was less than atmospheric pressure, then atmospheric pressure would push down more, and this side of the mercury would rise, right? If this pressure was lower than atmospheric pressure would push down on this mercury, and the mercury would rise on the other side. So I'm going to change this to correspond to what we've got in this problem. Let's take a look at this problem first. A gas container is fitted with a manometer. Good. The level of the mercury is 15 millimeters lower on the open side. Okay, so I'm going to redraw this to reflect what we just saw here. All right, so you can see that I've drawn the mercury, I've redrawn it in blue, and you can see that the level of the mercury is lower on the open side and higher on the closed side, okay? And it's 15 millimeters higher on the closed side, or 15 millimeters lower on the open side. Okay, same thing. So this is 15 millimeters, all right? Now, just to reduce any confusion, I'm going to white out the mercury that was in the diagram to begin with. All right, so this is really what we're dealing with. This reflects the situation that we're in. This is the gas in the container, and the manometer is open on the atmospheric side. It's experiencing atmospheric pressure. So if I was to write an equation that reflects what we're seeing here, we would see this equation. This would be our equation. The pressure of the atmosphere would equal the pressure of the gas inside the manometer plus the pressure exerted by the weight of this mercury. Okay, so that's 15 millimeters of mercury there. All right, that is going to correspond to 15 millimeters of mercury in pressure. So I'm going to rewrite this now. I'm going to add these numbers to this equation. All right. So here it is. The atmospheric pressure, 750. The pressure due to the weight of the mercury on this side, okay, is 15 millimeters of mercury. All units of pressure are the same here. We have 750 millimeters of mercury of atmospheric pressure and 15 millimeters of mercury pressure due to the mercury, right? So 750 minus 15, that's going to be 735 millimeters of mercury. That is the pressure of the gas inside the container. Let's try another one. Okay, so let's move on to number 10. I'm just going to read through this. A soccer ball is attached to an open-ended manometer, just like we see here. Mercury level in the manometer is 10 millimeters higher on the side attached to the ball. Atmospheric pressure has already been determined to be 770 millimeters of mercury. I'm going to redraw this, this little diagram to reflect what we're seeing in this problem. All right, so far this is what I've drawn. I erased the glass container and I redrew a soccer ball. It looks just like a soccer ball. And it's connected to the manometer, all right, so this U-tube. The U-tube is open. All right, so I want you to, before I draw anything here, we have 750 millimeters of mercury of pressure acting on this surface of this mercury, okay? And it's said in the problem here that the side of the soccer ball side, the mercury is higher. It's 10 millimeters higher on that side. So I'm going to redraw that to show this. But you can see how the level of this mercury is going to go push down. This level of mercury is going to go up, corresponding to what we've got in this problem. Okay, so I added the rest here. I changed the mercury. The mercury is now 10 millimeters higher on the soccer ball side. Okay, so if I was to write out this entire equation, I need to get a little bit more room. The pressure of the atmosphere equals the pressure of the gas inside the soccer ball. I'll say SB for soccer ball, plus the height of the mercury on the soccer ball side. So the pressure due to the mercury, which is in millimeters of mercury. Okay, filling this in then, 770 millimeters of mercury, atmospheric pressure, the pressure inside the soccer ball, plus the 10 millimeters of mercury. I'm just going to write MM, millimeters of mercury. I'm abbreviating it because otherwise I'm going to run out of room there. Just solving for the pressure inside the soccer ball, it is going to be 760 millimeters of mercury. So that's going to be the pressure inside the soccer ball. All right. Let's try a different one. Okay, so here's number 11. We have got this situation. We have an open-ended manometer, so the open end, of course, is exposed to the atmosphere. And it's connected to a canister. Here's our canister, filled with a gas. The pressure of the gas is at 771 inside the container. The mercury level on the side open to the atmosphere is higher. So that's a little bit different than last time. All right, I'm going to redraw this diagram to reflect what's in this problem. Okay, so here's our diagram redrawn. We have a pressure inside the container at 771 millimeters of mercury, and the pressure of the gas inside is now pushing down on the mercury here, causing it to rise on this side. Okay, and it rose 11.2 millimeters above the mercury level on the other side. Okay, so let's write down what we've got here in an equation. Here we go. Here's our equation. It's a little bit different than before. Now we have the gas pressure in the container higher. Okay, so the gas pressure in the container is going to have a pressure that is atmospheric pressure plus the added pressure of the weight of this mercury. Okay, so now we're going to solve for the atmospheric pressure. I'm going to fill in the equation, solve it. I'll be right back. All right, so I solved it. I put the numbers in, the corresponding values for these variables. and I solve for the atmospheric pressure. The atmospheric pressure, of course, is lower than the pressure of the gas inside. How do I know that? Well, because it pushed the mercury down and it pushed it up on the open side of the manometer. Okay, so this pressure, 759.8 millimeters of mercury plus the 11.2 millimeters of mercury equals the pressure of the gas inside the container. All right. So those are 3 problems solved for you. I'm going to ask you to finish this worksheet, and good luck.